अच्छा पहले आ गया हाँ
शेयर कीजिए।
ये चालू हो गया ओके चलो good morning to everybody. So I am very grateful to the organizers of sixth international conference on green materials and environmental engineering held on February 2021 at Changsha, China. And in fact, I could have become more happier had I presented it personally, and I could have seen Changsha also. But I am sorry that due to Corona, I am not getting that opportunity. So again, I wish that at some other time we will meet. Then my topic of the speech is investigation on the wire electrodischarge machining behavior of aluminosilicate particles reinforced A6061 alloy prepared by compo casting process. So in fact this is work done by my research scholar Dr. Abhijit Day, who is working as assistant professor at NIT Srinagar. Then the presentation outline that is following introduction, then literature review, inference drawn from literature, so objective of the present work, flow chart of the research work plan, materials used for the fabrication of AMCs, fabrication of the aluminum matrix composites, WED machining of the prepared composites, results and discussion, then morphology of AS6061, Senosphere AMC, effect of WED machining parameter on the responses, mechanism of WEDM of MMC, then optimization of the WED machining parameter, then conclusions, then scope of further research. So that is our profession, this presentation outline. Then about introduction. So what I will say that aluminum based metal matrix composites, that is AMCs we call, aluminum based metal matrix composites. They are widely used in automobile, aerospace and sports equipment industry due to its high strength, stiffness, wear resistance and improved damping capacity. And increasing demand of AMCs creates challenges to make mass production of AMCs at low fabrication cost. To achieve this objective there, has been gaining interest in reinforcements containing low density and low cost materials such as fly ash and natural minerals. Then presence of fly ash results in decrease that results in decreasing the density of composite and increase its strength to weight ratio. Then however, the processing methods influence the microstructure and mechanical properties of the MMC. The property enhancement of AMC requires the successful incorporation and distribution of the reinforcement particles into the molten matrix and are acquiring good bonding between them. Stir casting is the most widely employed liquid casting process to prepare AMCs where the matrix is completely melted and reinforcement particles are added into the molten metal. Wettability is the major setback in steel casting between the molten matrix and the ceramic particle. Then several techniques have been attempted to improve the wettability by many researchers, which includes adding wettability agents and fluxes, coating the ceramic particle and preheating the reinforcement particles. Implementation of those techniques results to increase the cost of fabrication. Hence, modified steel casting process route has been come to improve the variability named as compo-casting process, whereas controlled casting temperature, the reinforcement particles incorporated into the aluminum matrix at a semi-solid rate. Then AMCs produced by such processing technique are extensively used as structural material in aerospace and automotive industries. Several studies had been reported to enhance wettability and better distribution of reinforcement particles in the AL-based AMCs produced by compo-casting. However, the applications of existing MMCs are limited, whereas their machinability is a major concern. Poor machinability of the material results in poor surface finish and excessive tool wear. Then most of the time, the MMCs are difficult to be machined with high accuracy by traditional techniques due to possession of higher hardness and reinforcement strength. Hence, electrical discharge machining EDM process becomes feasible method that does not require any mechanical energy to remove the material from the work material. So compared to the WEDM, that EDM is slow machining process and required to elaborate preparation of precept electrode, that is tool. Then wire electrode discharging machining. WEDM is a highly established non-conventional machining process employed for manufacturing components with intricate shapes and profiles. Machining through WEDM is a technology with increasing economic importance in terms of units sold per year while comparing to die sinking EDM. The various parametric settings required in the WEDM process play a significant role in obtaining an optimal performance. The primary goal of the WEDM process is to achieve an accurate and efficient machining operation without compromise in the performance characteristics. The principal way to achieve this by understanding the interrelationship among the number of machining parameters affecting the performance characteristics and by identifying the optimal process conditions. So this is the literature around the topic, centered around this topic. So several attempts have been made by the researcher to explore the correlation between the machining parameter and performance characteristics during WEDM of MMCs. So we have put here serial number, then author and details, and then key findings. So in this area, work is done in 2006, then by Patil et al. And this is published in International Journal. Then Journal of Advanced Manufacturing Technology in 2010. Some other work is done related with this matter. So we observe that there is a huge amount of literature available in this area. So I would like to skip these slides, and this is just to show how many researchers work in this direction. And in fact, I want to concentrate over what objective we have taken. And then, so ultimately, inferences drawn from literature, it is thus realized that the studies related to die sinking, EDM characteristics, and MMCs are reasonably extensive while compared with the finding reported on with WED machining behaviors of MMCs. Though tool breaking, tool wear, and recast layer are the major issues. However, the investigations related to WEDM of MMCs reinforced with low density ammonia silicate particles have not yet been studied. Moreover, the issues related to wire breakage and poor quality of machine surface are still not described elaborately in any literature while machining these materials. Then, setting up optimal WED machining condition will require to be identified. Hence, this work provides the contribution through understanding the effect of process variable like pulse of time, percentage of reinforcement, and wire feed on the performance characteristics like cutting speed, surface roughness, and curve fit of compact stenosphere particle reinforced AS6061 LOI while machining through WDEM. Then objectives of the present work. So the following objectives have been set to realize intended goals. So we have taken the following objectives. That first one is to fabricate the sphenosphere particles reinforced A6061 metal matrix composites using compo-casting processing route. Second, to study the morphological behavior of the prepared composites. Third one is to study the machinability characteristics of the prepared AA6061 Cenosphere AMC employing wire indium. Then to investigate the effects of machining parameter on performance characteristics of the prepared composites while machining under WEDM. Then to study the ED machining mechanism of AA6061 Cenosphere AMCs. Then to develop an empirical model to study performance measure using response surface methodology that we call RSM, response surface methodology. So then multi-objective optimization of the process parameter for WED machining process using desirability function and GRA in conjunction with RSM. So this is flow chart of the research work plan. So, okay, so this is obvious. Then materials used for the fabrication of AMC, these are the following. That is matrix material, AS6061 is used as a matrix LY. It possesses good fracture toughness, machinability, weldability, brazability, and high corrosion resistance, and electrically and thermally conductive diffusion. Then chemical composition of aluminum LY, AS6061, this is given, that element, so what are the percentage of the metals it is having, this is displayed here. Then this reinforced material, Cenosphere fly ash materials. So hollow waste byproduct, these are hollow waste byproduct, very low electrical and thermal conductivity, SiO2, Al2O3, then Fe2O3, they are major constituents, and calcium oxide, TiO2, K2O, etc., these are minor constituents. So fly ash particles are classified into two types, that is Cenosphere and precipitator. Then this is particle size distribution, we can say, and this is FESEM micrograph and index pattern of Cenosphere fly ash particles. And this is fabrication of the aluminum matrix composite. So how they are fabricated, that is shown. And particles are the molten alloy, and here semi-solid melt after pouring in the metallic mold, and this is removable component from mold. Okay. And these are prepared composite samples. So this is self-explanatory. Okay. Then compo casting process parameters. These are the compo process. So these are the parameters like value we have set preheated temperature of the Cenosphere particles. If it value is 280 and temperature 280 degrees centigrade. Then preheated temperature of mold, it is 550 degrees centigrade. Temperature of the melt chart, it is 610. And stirrer speed, it is 550 rpm. Steering time, it is 5 minutes only. And particle speed, that it is zero point 0.8 to 1.3 gram per second. So how this is done, that the average size and density of Cenosphere particles were 800 micron and zero point 0.4 to 0.8 gram per centimeter cube respectively. The temperature of the induction furnace was maintained at 610 degrees centigrade. Stirring was continued till all the senosphere particles were mixed with the semi-solid aluminum. And then to enhancing the fluidity of semi-solid slurry, the pouring temperature was kept slightly higher than the casting temperature. Then this is experimental setup used to prepare the AMC, that is aluminum matrix component. So this is how we prepared, and this is the photograph of the machine. Okay, and these are the equipment which we use. Then composites were prepared from the castings is then carry out microstructural characterization. The composite samples were polished using standard metallographic technique and etched them with killer reagent. The each specimen were observed under high resolution optical microscope and FESEM equipped with EDS. Then X-ray diffraction patterns XRD were recorded using analytical X-ray diffractometer. The micro-hardness of the specimen was measured using a micro-hardness tester at 500 gram load applied for 15 seconds. So these are the equipment used for characterization. So this is FESEM equipped with EDS. This is cold molding for sample preparation, and this is KDM and okay. So these are the equipment which we use. Then this is tensile displacement as per ASTM, it is standard. So WED machining of the prepared composites. This is something about WED machining. So selection of machining parameters and performance characteristics. The study begins with considering all the possible machining parameters for the experimental analysis and employing one factor at a time, approach keeping all other at a constant value. Selected machining parameters are pulse on time, that is turn. Pulse on time is the time period when machining is performed. It is expressed in microseconds, µs. Then pulse of time, that is tau. Then pulse of time is the time interval between two consecutive pulses. It is also expressed in microseconds, µs. And third one is wire feed rate. Wire feed rate is the rate of the wire electrode travel. It is expressed in meter per minute. Then fourth is percentage of reinforcement. Then the most important performance measure in WEDM process are cutting speed, feed, KERF, cut width, and surface roughness. Then cutting speed. Cutting rate is measured by the length of the cut per unit time. It is also expressed in millimeter per minute. Curve width. Curve width consists the diameter of wire and additional gap on each side of wire after machining. It is exposed in micrometer. Then third one is surface roughness. So surface roughness is determined the standard of the finished product. It is expressed in micrometer. So just I am sorry, I will take 5 minute break, then I will speak. इसलिए हम तुमको बोलता है सुन सवेरे एक कप और शाम में एक कप पी ले बोलते बोलते कब चाहिए आपको दोस्त का भाषण देते समझिए ना हम बोलते बोल जाएंगे कि हम So, okay, so sorry for the inconvenience. Again, I am back. So, machining steps, these are the machining steps. Cutting speed is measured by the following formula. Cutting speed is equal to length by of slot, then divided by cutting time. Then machining of the slots of length 15 are different process parameters. Then cutting time is calculated by in a stopwatch. Then cut width of the slot is measured using optical microscope. Then surface roughness of the machine surface is measured using 3D optical profilometer. Then you can see the machining setup, that how this is done. So it's schematic diagram of WDM processed, then CNC electronic wire EDM machine, and this. So okay, so these figures are self-explanatory. And now I will come to result and discussion. So this is XRD pattern of CompoCraft A6061 square AMC. So we can see. So here, no formation of any intermetallic compound is observed. So on the x-axis, we see that angle is plotted 30, 50, and 90, and the intensity that is plotted this is on y-axis, that is 0 to 600. So okay, so this curve is also self-explanatory. Then this is morphology of AS6061 senosphere AMC, that is microstructure having dendritic arm. So this is the figure. Then next, this is optical photomicroscope micrograph of AL6061 senosphere AMC. So okay, these are the pictures. So here we have used four variables like 2% by weight is added, then 4% by weight is added, then 6% by weight is added, then 8% by weight. So four variations we have taken. Then this is same micrograph of L6061 stainless steel fly ash composite. So this is also self-explanatory. Then this is another figure. So this is about something about microstructure analysis. The microstructure depicts the dendritic structure caused by solidification. The habitual casting defects like slag intrusion, porosity, shrinkages, etc. are not found in the micrograph. Then, embodiment of stereospheric particles refine the microstructure of the aluminum matrix. The solidification pattern of the semi-solid composite slurry has influenced by the stereospheric particles, which could result in the grain refinement. So here we can see a clear interface exists between aluminum matrix and fly ash particles. It is observed then. No intermediate zone is observed surrounding the fly ash particle. Then pure interface is required to enhance the load bearing capacity. So this is EDS analysis of AS6061 fly ash AMC. So this diagram is also self-explanatory, and we can see that all the basic elements of fly ash and AS6061 are found, such as AL, MB, SIO, FE, TI, CU, MN, ZN. So this is EDS spectra of AS6061 stenosphere, compocup composite 6% by weight, then 8% by weight. So these are one is 6%, one is 8%. And here this is mechanical properties of AMC. So here we can see fly ash by weight, it is 0 there to 8%. And this is BHN, then UTS in MPA. Okay. So this is also self-explanatory. Then this is effect of WED machining parameter on the cutting speed. So this is also for 4% of weight. 2, 4, 0, 2, 4, 6, and 8. We have taken here. So this is also self-explanatory. Then variation of cutting speed with pulse on time. So what we observed in our experiment, this is purely experimental work. So with increasing pulse on time, more material removal takes place due to increasing duration of a spark. However, unreinforcement AS6061 alloy composite exhibits the highest cutting speed compared to the both reinforced composites. It is due to the fact that the fly ash particles are thermally and electrically non-conductive in nature, and therefore presence of fly ash reduces melting and vaporization of the composites. As a result, it obstructs the cutting speed during machining process. Then it is evident from the graph that the cutting speed decreases with the increasing pulse of time for all the three composite samples due to the fact that on increasing the time gap between the two consecutive sparks, the process of erosion of material becomes slower. However, 8% weight fly ash ASC061 AFC exhibited slowest cutting speed due to the presence of the utmost fly ash cut. Okay. It is found that there is no significant influence of wire feed on cutting speed for all the three composite displacements. Hence, it is recommended to keep the wire feed in a medium level so as to reduce the wastage of wire. Higher feed causes more wire consumption as well as more cost of machining. So here effect of process parameter on curve width. So again, this is something about curve width, and here on the x-axis we can see pulse on time in microsecond and curve width in it is given on y-axis. So variation of curve width with pulse on time. This is about discussion. So it is observed that as the pulse on time increases, the curve width of the composite also increase in order to discharge energy of the machining surface is high. Then the narrowest curve width is found in the composite where it became thinner as the fly ash content is increased. Then it indicates that the thermally and electrically non-conductive fly ash particles barricade the machining process compared to the conductive A6061 aluminum alloy. These results may be attributed to the fact that the thermal and the electrical conductivity of the composites are lower than the non-reinforced A6061 alloy, and so that high melting points of the fly ash particles have required much more thermal energy per unit volume to melt the reinforced composite than that of the unreinforced alloy. So this is another conclusion of this experiment about cut width. Then effect of process parameter on surface roughness. So this is also the graph is self-explanatory, and here we can see that pulse on time increases, the risk roughness of the machine surface of the composite increases due to the increased size of the crater. It is thus implied that the stenosphere particles of this composite protruded on machine surface and created poor surface integrity. Then variation of surface roughness with pulse of time. So we have done work in this area also, variation of surface roughness with pulse of time. And here we see that the fly ash content increases in the composite. It exhibits more roughness on the machining surface. It is because during higher pulse of time, the insulating phase is dislodged after melting of the surrounding matrix, hence the resulting craters are produced comparatively more roughness on the machining surface of the composite. So this is variation of surface roughness with wire feed. So here it was obtained from the figure that surface roughness increases with the increase in wire feed, and the trend is almost linear, but the effect is very small. So the figure 31, this is generated 3D optical surface of the machine sample for various percentage weight of fly ash content. Then mechanism of WEDM of MMC. So here we see that the existence of reinforcement particles makes the process slower and initiates additional complexity. Then, in the present study, there might be occurrence of different kinds of situations such as the particle is completely inside the slit width, that is PCSW. Then the particle is partly inside the matrix and partly inside the projection required diameter, that we call PPWD. Then third one, the particle is partly in matrix and partly in melted material, that is PPMM. So this is graphical representation of the typical wire EDM process of AEM. Then case here we have analyzed PCSW. So the xenospheres, which are completely inside the slit width, are initially barred from the matrixal wires such as material in front, and sides of the reinforcement particle begin to melt and evaporate. And ultimately, the protruding portion of the xenosphere particles may generate some, let me say, in the surface of wire, which leads to abnormal failure of wire. Then this is the detailed analysis about this, and we have all reported in the research paper, and all the research papers are published. So we have published many in good quality international journal papers in with this work. And first, let me come to that because here the time limit is 40 minutes, so I want to finish this. So, first of all, I will explain these things later and what conclusion I got that I should tell. And this is the case about PPWD. So here we have an I, the PPWD also. So we can see it from the diagrams and this PPMM that here the sphenosphere partly in matrix and partly in melted material. This is the case. So these cases also we have analyzed it. And these are the diagrams. And tool wear and breakage. About this, we have studied that the wear of the wire electrode increases with the increase of the weight fraction of reinforcement and pulse time. Then this occurrence was attributed to the relative increase of energy discharge with the increase of pulse in time. In addition, generation of aberrant arcing, the interaction of the non-conductive reinforcement particles with the wire electrode increases as the percentage of reinforcement increase, which results in higher wear rate of the wire electrode material. So these are the, again, graphical representation about pulse on time. And the image of the electrode surface. This is about discussion. So therefore, we have come to this conclusion that for effective WEDM of MMCs, large current and short on time have been recommended because the wear rate of the tool wire reduces at higher flushing rates because of higher cooling rate of the wire electrode, and a low wire feed rate allows the wire to withstand higher discharge energy per unit time, which expedites the breaking of the wire material. So this is about surface finish and dimensional accuracy. So the generated machining surface of the prepared composite is composed of many microscopic craters accomplished with indiscriminate discharge of spark between the electrodes. The valleys and their adjacent peaks in the crater structure of removed material is clearly conspicuous. So we can see it from the diagram figures. Then estimation of regression model by RSM. So this is computational work. So a response surface methodology, RSM, is a collection of mathematical and statistical techniques useful for analyzing problems in which several independent variables influence a dependent variable on response. The goal is to optimize the response. And the work is done in 1962. So this is computational work. So these are the basic equations. And this is design of experiment. So these are the experimental results. And these are ANOVA tables for CS, that is modeling of the performance characteristics. This is the response surface equations for CS. This is also self-explanatory. And this is the response graph of cutting speed. This is modeling of curve width and ANOVA tables for curve width. This is given. Then response surface equation of curve width. And this is the response graph of curve width. Then this is modeling of surface roughness, measure, ANOVA table for surface roughness. response surface equation for SR, then response graph of surface roughness. Then desirability, optimization of WED machining parameter, desirability function based response surface methodology. The goal of optimization is to find a set of conditions that will meet all the goals. And it is not necessary that the desirability value is 1.0, as the value is completely dependent on how closely the lower and upper limits are set relative to the actual optimum. So this is ramp function graph and bar graph of desirability. Then we have come to some conclusions about this, that desirability 3D plots were drawn by keeping the input parameters in range and output response is at maximum, KW at minimum, and SR at minimum. So I am skipping some explanation just to save time because I want to finish the lecture in time. So this is about 3D surface graph of desirability. The interpreted desirability of 0.741, which indicates the closeness of the response target. So this is plot of the actual versus predicted values. Then 3D optical surface image of the confirmed surface sample. In order to observe the better resolution of the finished surface, the sample of the confirmation experiment were investigated using 3D optical surface profilometer. Okay, so the figure is self-explanatory. We can see it. Then we are coming up to conclusion, main conclusion, that research in non-conventional machining of particle reinforced AMC is still developing, though it has made good progress in few areas. The presence of reinforced particles adds additional complexity and makes the machining process different from that of monolithic matrix material. The present research focus to investigate the microstructure and machinability study of compacted and stenosphere reinforced AS6061 alloy through WEDM, and the following conclusions has been drawn. So conclusion number one, that is, there was no formation of any intermetallic compound due to interfacial reaction. The fly ash particles were thermodynamically stable at the compacting temperature. Second, the fly ash particles were dispersed homogeneously in the AMC. The interface between the aluminum matrix and fly ash particle was clear and the bonding was proper. The addition of stenosphere particle enhanced the micro hardness and tensile strength of the AMC. WEDM cut A6061 LY and 0% weight percent. Stenosphere composites obtained the highest cutting speed than the other 2%, 4%, 6%, and 8%, AS6061, and 6% by weight and 8% both AMC material yielded almost similar cutting speeds. Additionally, increasing the weight fraction of reinforcing stenosphere particles facilitated the breakage of the wire material. Then the other conclusion. We can see that the width of the slit of the cut sample progressively trends to narrower as the weight fraction of stenosphere reinforcement in the composite increases. The narrow width of slit led to difficulty in repulsing debris particles from the craters of machine zone into the dielectric media. Protruding stenosphere particle within the discharge gap hindered the advance of the brass wire along the path of machining, resulting the brass wire to shift. Thus, obvious bindings were observed on the machining surface when the 8% by weight AS606 stenosphere composite was machined. This occurrence was appeared under low wire tension, but such features were generally absent from machine surfaces generated under high tension of wire cutting conditions. Then, These are the other conclusions we can see. The tensile strength of the brass wire reduces drastically due to the softening at high temperature during WEDM, causing the breaking of wire electrode. Further research will be devoted to developing a new material which poses a resistance to creep wire at high temperature. Then, with increasing pulse on time, more material removal takes place due to increasing duration of sparking, which leads to enhanced the cutting speed. However, fly ash particles are thermally and electrically non-conductive, and therefore presence of fly ash reduces melting and vaporization of the composites. As a result, it obstructs cutting speed during machining process. Okay, so we can see that the predicted values of R square for CS, KW, and SR match reasonably well with the experimental values. Means computational work, this is matching with experimental results. The, the finding of the research along the derived mathematical models and multi-objective optimization will provide effectual guidelines, and the outcomes will be an essential technical database for the automobile, aerospace, and military application in manufacturing and machining aspects. Then scope of, so those were the conclusions of our research work, and the scope of further research here it is discussed that although the WEDM has been thoroughly investigated for xenosphere reinforced aluminum metal matrix composites, still there is scope for further investigation. The following suggestion may prove useful for future work. That efforts should be made to investigate the thickness of recast layer which is influenced by the processing parameters. Second, the tribological behavior of fly ash sphere particle reinforced aluminum alloys is of prime importance in aluminum AMMC research. Then no significant research work in this area is reported till date in the literature. Then efforts should be made to investigate the effect of EDM process in a cryogenic cutting condition. That is also yet to be done. And we have got in this work, we have got good list of publication, like we could publish many SCI journal papers, like one paper it is published in one review paper in Review Advanced Material Science with title Characterization of Fly Ash and its Reinforcement Effect on Metal Matrix Composites, a review. Then second, that is work, real work, it is not review work, that is wire electrical discharge machining characteristic of A6061 Senosphere cast aluminum matrix composite. This is published in Materials and Manufacturing Processes, Taylor and Francis Journal. This is SCIA. Then we have published another machinability of Senosphere particle reinforced A6061 aluminum alloy prepared by compo casting, part B, Journal of Engineering Manufacture. So this is also SCI journal. Then another optimization of medium process parameters for AL6061 Senosphere compo using gray weft hybrid approach. Then this is transaction of non-materials, non-ferrous material. So this is a SCIE journal. And then other also that it is also now published. So these are the journal paper we have So we have published many journal paper on this topic with this work, and we have published some in scope of index paper also in materials today, and we have published in SEEP also one conference held at Blade in Slovenia, and I presented two papers there. So ultimately, I finished with this, and I will be happy to get questions by email, and I will be in a position to, and I will say that in fact, I do research in combustion area, but my interest lies in manufacturing sciences also, and so far I have guided two PhDs and many MTech students in material manufacturing sciences, and still some students are working with me in manufacturing area, and my interest lies in manufacturing sciences also, because there is a good amount of chance of doing good research in this area. So again, I am very much thankful to the committee for giving the opportunity, and I thank everybody, and I will be happy to answer questions by mail. Thank you very much. Have a good day.